Well, it's Monday after your grad weekend. I know it probably wasn't the typical grad weekend with lots of craziness and festivities, but either way, hopefully you had a great time. And I thought today we would not be learning any new material, just reviewing the first few days of our acid-base equilibrium unit. And I was just doing my timeline, and I believe there are 7 lessons left plus an assignment quiz day. So about 8 days, maybe one more to finish off. So end of next week and we are done, finished, finito. I can hear the cheers in the background. Amazing. So today is a review day. I'm going to go through key stuff that we learned in the last few days, and then you're going to have a lab assignment to do at the end of the lesson. So let's dig into it. Just that. Okay. So you should be able to take any acid or base and predict using Bronsted-Lowry theory. What do these things look like in water? So sulfurous acid is H2SO4 or SO3 aqueous in water. So because we know it's an acid and Bronsted-Lowry theory says it will donate a proton, probably stuck in equilibrium, we'll figure that out, and donating a proton, an H plus, so we lose an H, so we're HSO3. We lose a plus, so we're HSO3 minus. Water gained the H, so it's H3O, and it gained the plus, H3O plus. So there's our hydronium ion, which is why it's acidic, and there's the leftover anion. If we wanted to use some more terminology, this is an acid, this is a base. If this is an acid, this is its partner, conjugate, which means partner, conjugate base, and that means if this is a base, this is its partner, conjugate acid. Okay, percent reaction, the rule is when you have a weak acid in water on the table of relative strengths, all the weak acids are below water. So they always react less than 50% using water as the base and any weak acid. Let's just jump to that table of relative strengths. So here's water. And every weak acid, starting with oxalic acid and going down the list, they're all below water, so they're all less than 50%. Okay, sulfuric acid in water. Sulfuric acid is H2SO4 aqueous. In water, again, it's going to look the same using Bronsted-Lowry theory. Acids donate a proton. And we get HSO4 minus as our conjugate base and hydronium. Okay, percent reaction. Sulfuric acid is one of the big 6. It is a strong acid. So the big 6 strong acids are the only 6 that can go greater than 99%. You could also show this as a single-headed arrow. It is quantitative or complete. So if we did some math on it and we had 3.5 molar, we would get 3.5 molar, 100% product. So you can predict pH very easily if you know the concentration of your strong acid. Sodium cyanide. Okay, so sodium cyanide is an ionic compound, so we need to dissociate it. And once we dissociate it, hopefully you recognize that Cn minus, like most anions, is a base. And if you weren't sure, you could go and look it up on your table. And you would find it. There it is, right there, in the conjugate base column. So it is a weak base. And a weak base will react with water as the weak acid. And weak bases in water are also less than 50%, same as acids, Bronsted-Lowry theory. They accept a proton. So water is the acid donating, Cn minus is the base accepting, HCN and OH minus. So the Cn minus gained the H plus. It was a weak base. This would be its conjugate acid. Water is the weak acid. This is its conjugate base, and that's why cyanide is a base, because it makes hydroxide in water. Got it? Sure you do. That's kind of a cool looking smiley face. He's got that sort of demure, aloof, sly smile on the go. I know, it's amazing what I can read into my own art. Truly gifted. Okay, determine the pH of 2.5 mole per liter hydrogen iodide or hydroiodic acid. So hydroiodic, if you're not sure, let's just go take a look on here. And you will discover, oh, it's one of the big six. It's a strong acid. So that means that in water, it goes 100% to hydronium. And I minus, not C minus. 100%. So, or greater than 99, you'll see both. If we had 2.5 mole per liter, we are going to get 2.5 mole per liter. So calculate the pH of that. So formula is pH is equal to, negative log of concentration of hydronium. So negative log of 2.5. And I forgot to pre-do that one, so I'll do it right now. Negative log 2.5 is negative 0.397398. That is a very low pH. And 2 sig digs, so I go 2 decimal places. Negative 0.40 for the pH. Okay, determine the pH of 2.5 mole per liter solution of strontium hydroxide. Whoops, there's my 2. SrOH2. So SrOH2 is able to dissociate into 2 hydroxides. So 2.5 mole per liter SrOH2 produces 2 hydroxides for every 1 SrOH2. So we get 5 moles per liter of OH minus. It's a strong base, strong ionic compound. Ionic compound dissociates 100%, and we get a strong base. So that's our concentration of hydroxide. We want to get the pH. So you've got 2 choices here. You can do POH and then pH, or you can use KW to get hydronium, and then once you have hydronium, you can get pH. So however you want to attack this one. So I am going to go negative log of 5. And that gives me the POH. Negative 0.699. And that's 2 sig digs, 2 decimal places, negative 0.70. That's POH. I didn't leave enough space. pH is 14 minus POH. Hopefully this is all coming back to you, which means 14.70, 2 decimal places for our sig digs. So that's a very high pH. That's a very basic compound. Hey, we're half done our review. Oh, are we half done? I think so. Short today. Okay, what is the hydronium ion concentration and the exact percent reaction for a 2.5 mole per liter solution of nitrous acid that has a pH of 2.10? That's a lot of information. 2 sig digs for 2 decimal places, 2 sig digs. Okay, nitrous acid, HNO2. Nitrous acid in water does not react 100%. It's a weak acid, so it's stuck in equilibrium. This is what we're interested in, but we do not know the percent reaction. We just know it's less than 50%. But we can get this from the pH. So concentration of hydronium is 10 to the negative pH. Isn't this stuff fun? Yes, it is. Okay, 10 to the negative pH. I think I did this one. course, it's a bunch of calculations back now. Okay, so 10 to the negative 2. I changed. Oh, no, we're good. Okay, 10 to the negative 2.1 is 0.00794. So there's our ... concentration of hydronium ions. Okay, so that's done. And that's mole per liter. Okay, and then we want the percent reaction. So percent reaction is the amount of product over maximum possible product, right? So what did we get? Well, the amount of hydronium we got was 0.00794 ... out of a possible 2.5. So if we'd had 100% reaction, we'd have 2.5 divided by 2.5 and then turn it into a percentage. We got way less than 2.5. So this is a very small percent reaction, and it works out to be 0.32%. 0.32%. So that is a very weak acid, as most weak acids are, with only very partial ionization in water, 0.32%. So when we say they're less than 50, they're usually way less than 50%. Okay, last topic was five-step method with Bronsted-Lowry theory. So predict the products of these reactions and their percent reaction. And to do the approximate percent reaction, we need that relative strengths table where we can look up greater than 50 and less than 50. Okay, sulfurous acid, H2SO3 aqueous. It's a molecule, so we'll leave it together. Sodium sulfate is an ionic compound, so we'll dissociate it into sodium and sulfate ions. And because this is aqueous, we also have water. So there's all our possible players. We go look them up and discover weak acid, spectator ion does nothing, weak base, and water is both a weak acid and a weak base. So we have to go through and find the weakest acid and the weakest base and then react them. Okay, H2SO3, SO4 2 minus. So H2SO3 is right there. So that's fairly strong as far as weak acids go. And SO4 2 minus is right there. Okay. And there's water. So our strongest base is SO4 2 minus. And our strongest acid is H2SO3. So H2SO3 is the strongest acid, and SO4 2 minus is our strongest base. Water is out on this one. So Bronsted-Lowry, react the strongest acid with the strongest base. Transfer the proton from the acid to the base. We'll look up percent reaction later. So we get HSO3 minus, it's lost its plus and H. SO4 2 minus gains the H and gains the plus, so it's now 1 minus. And if you check charges, they're conserved. That says a charge of 0, 2 minus, a minus, and a minus equals 2 minus. So we're good. Charges are balanced. Okay, all we have to do is percent reaction, and the acid is above the base, so it's greater than 50%. Favors products. So on a side note, just so you get an idea of where we're heading, later on, we're going to set these up as ice tables with equilibrium constants, and then you can predict the actual concentration of product using the equilibrium constants. Isn't that exciting? You will notice in our data book, oh my gosh, all of these acids and bases have Ka values. If I scroll down, look at that, Ka, the acid ionization constant. So we've done Kc, Kw, now we're going to do Kas and Kbs. So that's just something to get you excited about where we're headed and how we're going to put all this knowledge together at the end of this chapter. Yay. Okay, solid ammonium cyanide, last one. Ammonium cyanide is an ionic compound, so we dissociate it. It's high solubility. Everything is in this chapter. And water, and that's all we've got. So we got to go look these up. Ammonium cyanide and water. We know water is a weak acid and a weak base. Ammonium and cyanide. Okay, I think they're both down near the bottom. There's ammonium. It's a very weak acid, but it's still stronger than water. So strongest acid is ammonium. And there is cyanide, strongest base, and it is above the acid, so less than 50%. Cyanide is still stronger than water as a base. It's a pretty strong base, actually. Okay, so less than 50%. I got to remember that. NH4 plus is our acid reacting with Cn minus, our base. So the acid donates a proton to the base. And that means we get NH3. It's lost an H and a plus. HCN, it gained the H. It was a minus, it gained a plus, so now it's neutral, 0. And we said the acid was below the base, just barely, so it is less than 50%. Just going to verify that. Yes, the acid is below the base. Okay, less than 50%. So this one favors reactants. If this is the acid, which of these is the conjugate base? Acid, conjugate base. Base, conjugate acid. Those pairs, they differ by a single proton. Okay, and now your assignment for today. Normally we would do a lab, and your homework would be to do all the predictions for the lab, and then the next day we would go out in the lab and try all these reactions and see if they work. So you will only be doing the predictions, and you're going to do predictions for numbers 1, 2, 3, 4, and 7. So you've got 5 of these to do. For your predictions, you are basically doing what I just did right here. So you're going to use the 5-step method, and you're going to identify the strongest acid, strongest base, react them with correct products, and classify the reaction as greater than 50, less than 50, or greater than 99 as a third option as well, if you have strong acids or bases. So I've enlarged these reactions right here. So here they are, and it was 1, 2, 3, 4, and 7. 1, 2, 3, 4, and 7. So we're not going to do 5 or 6. We're not going to do 8 and 9 and 10 that are in your textbook as well. Just those 5. So I'll attach this as an assignment as well so that you can hand it in to me through Google Classroom. You're going to create a PDF image of your 5 reactions written out using the 5-step method, and I'd like you to get that into me today ideally, but you can have Tuesday as well. Just remember that on Tuesday we're starting our new material in this chapter, so you don't want to get behind. Okay? Have a great day. I'm going to step out of the mold here and put 1 extra strand of hair on there just because. Okay, we'll see you guys tomorrow. Have a nice afternoon.